Hello friends! In this video we'll build a very simple C++ program that finds the square of a number. At first glance this looks tiny, but underneath, this is one of the first examples of how programs transform input data into computed results. Now mathematically, squaring just means multiplying a number by itself. So 5 squared becomes 5 times 5, which gives us 25. Pretty simple. But here's the interesting part. Inside the computer, the CPU is not thinking about square as a special mathematical idea. It only sees instructions like load a value into memory, multiply two integers, and store the result back. Programming often works exactly like this. Big abstractions are built from very small machine operations underneath. In this slide we're setting up a variable called number, then multiplying it by itself to produce the square. In the next slide, we'll look at the complete program structure and understand what each line is actually doing. Now here's the full program. We start by including the IOStream library. That simply gives the program access to input and output features like cout. Then we enter the main function. Think of this as the program's starting point. When the operating system launches the application, execution begins here. Next we create an integer variable named number and store the value 6 inside it. After that, another variable named square stores number, multiplied by itself. This tiny multiplication line is doing the real work. The compiler eventually converts this into machine instructions that the processor can execute directly. Even simple arithmetic in C++ eventually becomes low-level CPU operations, moving through registers and arithmetic logic units. Finally, cout prints the result to the screen. So the program takes a value, computes its square, and sends the final output to the console window. In the next slide, we'll run the program and understand what the output actually represents. When we run the program, the output becomes square equals 36. That result comes directly from multiplying 6 by 6. This might feel extremely basic, but this exact flow appears everywhere in computing systems. Data goes in, the processor transforms it using instructions, then the result moves somewhere else. That somewhere else could be a console window, a game engine, a browser tab, or even a machine learning model. And here's something subtle people often miss. The computer never sees 36 the way humans do. Internally, that value exists as binary digits stored inside memory and processor registers. The arithmetic logic unit performs multiplication electronically using transistor circuits, switching billions of times per second. So even a tiny beginner program already touches the entire computing stack: programming language, compiler, operating system, CPU instructions, and hardware logic underneath. In the next slide, we'll improve this program so the user can enter any number dynamically instead of hard-coding it directly into the source code. Hard-coding numbers works for testing, but real programs usually accept input dynamically. That's why we use C in here. The program now asks the user to enter a number. Whatever value gets typed into the console is stored inside the variable named number. Then the same multiplication logic runs again to calculate the square. This is where programs start becoming interactive. Input changes the program's behavior at runtime, without changing the source code itself. Underneath, the operating system is coordinating keyboard events, buffering input data, and passing those values into the running process. Even beginner console programs are quietly interacting with system-level services behind the scenes. If the user enters 8, the program multiplies 8 by 8 and prints 64. If the user enters 12, the result becomes 144. The logic stays identical, only the input changes. In the final slide, we'll quickly summarize the full idea and connect it back to how computation actually works underneath. So in this video we built a simple C++ program that finds the square of a number. We started with a fixed value, then improved the program by accepting user input dynamically. Along the way we also looked at what the computer is actually doing underneath, loading values into memory, performing multiplication through processor hardware, and printing results back to the console. And this is why even tiny beginner programs matter. Small examples expose the exact same computational pipeline used by massive real-world systems. The scale changes, but the core idea stays surprisingly similar. Once you understand how data moves through a simple arithmetic program like this, larger programming concepts start feeling much less mysterious. Alright friends, that's it for this video. In the next one, we'll continue building on these basic C++ fundamentals, step by step.